Hello guys, this is Isaac, and today we are going to talk about two-sample t-test. There are two types of two-sample t-test actually. One is the situation where we have paired sample. And the other case is that we have two sample, but they are independent. So independent samples. And first, I want to talk about the paired sample t-test. So let me just erase this. And first, I want to talk about what does the paired sample means. Okay. Since we have two sample, it means that we have two group of data. So let's say we have group 1 and group 2. Since we are having like two sample, means like one sample consists of multiple numbers. So let me just write it out, some random numbers. So we have like 50, 145, and maybe 170. And in group 2, we have like 140 and 144 and then 165. Okay. And so these are we can say like this is group 1, and we say this is sample 1, and this is group 2, and we call that sample 2. So we have two sample. But when we say these are paired samples, then that means we can construct one-on-one relationship between the two groups. Between the two groups. So what does that mean? So one of the typical structure of the paired sample data is before and after measurement data set. Okay, so let's say this group 1 is actually the collection of the weight of people. So this is weight before smoke. Not let's say weight before workout. Weight before workout. And group 2 is the collection of the numbers, and that number is actually represent the weight of people after the regular workout. So a context is like this. So we have 3 people. So we have person 1 and person 2 and person 3, and we want to study the impact of the workout on our weight. So before we ask them to do the workout regularly, we just measure their weights first. So this 150 is actually weights of person 1, and 145 is the weights of person 2, and 170 is the weight of person 3. And after maybe several months, we measure the weights of these 3 again. So this 140 is also like related to the person 1, and this 144 is related to the person 2, and 165 is related to the person 3. Okay, so in that sense, we can think these two number 150 and 140 as a pair, okay, because they are related to, both of them are related to the person 1, and 145 and 144 become a pair because they are related to the person 2. So as the 170 and 165, okay. So we call this structure of data set as the paired sample. So we have 3 paired sample, right? So usually when we have paired sample data, since they are correlated, since they are connected with each other, we can make a one variable. So let's say we want to test the impact of regular workout on our weight using this symbol. So mu b is the mean of the weights before they start the workout, and mu after, so mu a represents the mean of the weights, mean weights after the regular workout. And if these two numbers are the same, then it means that the regular workout does not affect to the our weights, okay. And this one, alternative hypothesis, means that if the regular workout affects our own weights, and usually we are expecting that if one person do the regular workout, their body weight could be decreased. So we are expecting the mean of the body weight is larger than mean of the body weights after workout. Okay, does it make sense? So this null hypothesis means that regular workout has no effect on our body weight, and alternative has the opposite. Okay, so we do have the regular workout does have some effect on our body weight. Okay, but if we think about this equation, we can rewrite this equation as like this: mu b minus, so I'm gonna move this one, mu a, on the other side, so that makes the negative mu a. So mu b minus mu a is equal to 0, and this alternative hypothesis also can be written as mu b minus mu a is larger than 0. Okay. Let me just change this inequality into not equal, because maybe some of them, if they regularly work out, maybe they got some muscle and their body weights maybe actually just increase. So we want to determine that the mean of the weights after workout is not equal to the mean of the weights before workout. So I would say this one versus this one. And also, when we think about this thing, we have direct observation of this difference between the mean weights before workout and then after workout, like difference between the paired number. So for example, in here we have 150 and 140 as a pair, so difference between before weights and after weights is 10, right? So 10 can be obtained by 150 minus 140 is 10, right? And then the other one is 145 is the before weights, and 144 is the after weight. So difference between these two is 1, and this one is also 170 minus 165 makes the 5. So we have 1015. That 1015 is a direct observation of this parameter, right? So let's say D1 is 10, D2 is 1, and D3 is 5. Since we have the direct observation of this one, we can actually this thing as a new parameter, one parameter. So I would say maybe this one is the average or mean of the difference between the weights before and after workout. So I'd say maybe mu d, right? So our null hypothesis can be converted into like one parameter. Mu d is equal to 1, and since this one we already defined this thing as a mu d, so I would say mu d, our alternative hypothesis is like mu d is not equal to 0. Then this is the one sample t-test, right? So our null hypothesis is the mu d is equal to 1, and our alternative hypothesis is mu d is not equal to 1, and our real data is 10, 1, 5, not like 150 and 140, 145 and 144. Instead of these, we having only 3 numbers, right? So using this, we can do the one sample t-test. Okay, and what I want to do, I actually bring a real data set, and it's related to the long performance. Okay, so we have 20 people. So let me just change the screen. So this is our my description of my data. So we have 20 people, and then they are willing to participate the research about the impact of smoking. Okay, and we want to figure out what is the impact of smoking on the one person's long performance, and we measure their lung performance through the FEV1, which represent the first expiratory volume in 1 second, and that measures the how much air a person can blow out in 1 second. So it means that if someone has a higher FEV1, it means that, they have like strong or healthy lung, right? And we measure the before and then after FEV. So FEV1 before means that they just measure the lung performance before the smoking, and then this 3.55 means that the FEV1 after smoking, which connected to 3.40. So in that sense, these two numbers become a one pair. Okay, and this second row become a one pair, and our hypothesis can be written as this one. So mu1 and mu2. In here, mu1 indicates the mean of FEV1 value for non-smoker, and mu2 is the mean of the FEV values for smokers. Okay, and as I explained before, I can convert this one into this equation, and then we can treat this mu1 and mu2 as a one parameter, like mu d, right? And in SAS, we already did this one. We already did the one sample t-test using SAS before. So let me just copy and paste this code and then pull up the SAS. Okay, let me just pause a little bit here. Okay, so I pull up the Sas screen, and then I'm gonna paste the Sas code here. Okay, so first line is the data smoking. So I'm gonna declare my data set as a smoking data set, and then we let the Sas know that there's two columns in the data set, which is before and the after, FEV1, right? Measurements. And using these two, what I want to do, I want to make another column named DIFF, right? And this column can be obtained by second column, like after measurement minus before measurement. Okay, so this DIFF can be calculated by using these two columns. Okay, and data lines in here, what you can do is just go to my website. So let's just see. Okay, go to my website, and then just copy and paste, copy the data into sets here. Okay. Okay, so let's see. So if I submit this, we don't have any error, so it means that Sas can load the data without any problem. So let me just quick check the data set. So proc print data is equal to smoking, and run. If I just do this, I can see the data set. So we have before column, which has the numbers in the my first column in my data set, and then after column, and the different DIFF column can be obtained by after this, like, so for example 0.5. Let me just magnify a little bit. So this 0.15 can be obtained by 3.55 minus 3.40. Okay, so this DIFF column become our new data set. We don't care about these two. We only care about DIFF column. So we have one column, and that data set has 20 data points, and using this I want to do one sample t-test. Okay, and that t-test we can use just proc univariate data is equal to smoking, and by setting our interest variable as a DIFF, this proc univariate only using the DIFF variable. Okay, so if you run this code, you will get a lot of table, but there's this one, test table, and this test table says that our null hypothesis is the mu0 is equal to 0, which means we already set our DIFF variable as our interest variable. So the mean of this one we can think as mu d, and null hypothesis is mu d is equal to 0, and our t-test statistic is negative 4.06, and whose corresponding p-value is 0.0007, which is way less than, like, I don't know, your maybe popular significance level, such as 0.05. So I would say we can reject the null hypothesis. So which means there's a difference between the smoker and the non-smoker with respect to the what is the measure, FEV1 measure. So smoking, we can say that smoking has an impact on the lung performance of the people. Okay, there's another useful command in Sas that can do the two-sample paired t-test, which is a Proc T-Test. Okay, so when you use the Proc T-Test, we can declare our sample is a paired sample using this paired option. So in our smoking data set, we have 3 columns actually, but after column and the before column, they are connected, right? So we can write it down this one to declare, hey, these 2 columns are paired. Okay, and then if you run this code, if you submit this, it will show you a lot of plots and the result. Okay, but I want to look into the first 3 tables. Okay. So first we have 20 for n. It means we have 20 data points, and that can be connected with we have 20 people, right? Even if we have 2 sample, we have 20 paired sample, right? And we have negative 0.6055 as our mean. So it means that if we take the sample average of DIFF, we get this negative 0.6055, right? And standard deviation is 0.667, which means the standard deviation of, so sample standard deviation of the data is 0.6670, and standard error can be calculated by this standard deviation divided by square root of 20. Okay, and since we have a 20 data point, we have a degree of freedom as like 19, and if you calculate the t statistics, we get negative 4.06, and if we calculate the p-value, we have 0.0007. Okay, so maybe I want to recap everything using the new note. So let's say we have after column and the before column, and we have made one more column whose name is DIFF. So we have, let's say, 150, 145, and our DIFF can be calculated by 150 minus 145, so 5. Okay, and we have here is 20 numbers. We have 20 numbers, and we have 20 numbers here, right? So we have 20 numbers, and let's say this is D1, and the last one should be D20. And since our table shows this one, it means that if I take the average, so DI plus D20 divided by 20 is the negative 0.655, and if I take the standard deviation, so standard deviation of D1 through D20, it will be 0.6670, and standard error error is nothing but this let's say this is small sigma, sample standard deviation divided by square root of n, so which is 0.6670 divided by 20 will give you the 0.1491. And T statistic is nothing but this is x bar, right? So let's say since we have D, let's say this one is D bar, then D bar minus our null hypothesis mean, which is 0, divided by standard error, which is S square root of n, will give you the T statistic, which can be written as like this. So we have negative 0.655 as our D bar, and negative subtract 0, and we have 0.1491. And if you calculate this, you will get negative 4.06, which is this one, this value. Okay, and if you calculate the p-value using degree of freedom 19 in the t distribution, you will get very small p-value, so we can reject the null hypothesis if our significance level is somewhere around like 0.05. So one of the things you can notice is that our p-value is 0.0007. Okay, this is very small, and let's say our significance level is like 0.05. Then our significance level is way larger than 0.0007, which is our p-value. In this case, we can reject null hypothesis. Okay. However, let's say there's another situation. Our significance level is really small, such as 0.0001. Okay. If our significance level is like less than our p-value, then we cannot reject. So cannot reject H null. So whether we can reject the null hypothesis or not, it depends on your significance level. And when you try to solve the problem, you should get the information about the significance level. And most popular significance level is 0.05. So if I use this significance level, then since my p-value is way less than my alpha, so I can reject the null hypothesis. Okay. So let's move on to another topic, which is the case where we have independent to sample data. So this is the independent sample. So we don't find any one-on-one relationship between the groups. And our concrete example of this independent sample is about cloud seeding. And I attached this video which will explain about what is the cloud seeding. And what people is doing, that they seed the chemical into the cloud to have more rain. Okay, so I think it's a really interesting video, so I recommend you guys watch it, and let's see what our data looks like. So we have two columns. So let me just magnify it. So we have two columns. First column name is rainfall, and the other one, second column, is seeded. And this seeded column has the it's not numerical variable. It has two possible choice, S and U, and S represent the seeded, and U represent the unseeded. So there are two groups. So if I write it down, the data, we have rainfall and the seeded. And first, let's say just 1697 and 29, 17, 274, 118, and we have some numbers. And for seeded column, we have S, U, U, S, S, and so on. And we can convert this data into two groups, right? Group 1 is related to the seeded group, and group 2 is related to unseeded group. So the very first number in the group 1 will be 1697, and second one is 274 and 118, and for the unseeded group we have 29 and 17 and so on. So we have two samples from two different groups, and since they are independent sample, which means we don't have any relationship between these, so there's no relationship. So if we think about the information that we can grab using these two samples, one is, let's say x bar is the average of group 1. So we're gonna have x1 bar, and let's say average sample mean of the group 2, I will use the x bar 2. Okay, so this is a group 2 average. And also we could have S1 and S2, which represent the sample standard deviation for group 1 and group 2 respectively. Okay, and also we're gonna have N1 and N2, and this is the number of data points for each group. So N1 is the number of data points in group 1, and N2 is the number of data points in group 2. So they are not necessarily equals to each other. Okay, so we'll have these 6 information, and what we are going to do, what we want to test is that still we want to figure out maybe mu1 is the mean of the group 1, and mu2 is the mean of the group 2, and we want to test these two are the same. And alternative, maybe we can say that these two are not the same. Okay, and this one also can be written as like this. Mu1 minus mu2 is equal to 0, and mu1 minus mu2 is not equal to 0, something like this. And when we think about this term, do we have any direct observation for this the whole mu1 minus mu2? No, because we don't have any one-on-one relationship. Only thing that we can calculate, only information that we can use for this whole thing, we have x1 bar for mu1 minus x2 bar for mu2, right? So this is the best way we can use for estimating this whole thing. Okay, so this is the difference between the paired sample data and the independent sample data. So in paired sample, we have a direct observation for this whole thing, like D1 and D2 and then Dn, right? However, in here we only two numbers for estimating this whole thing, which is x1 bar minus x2 bar. Okay, and since we are doing the t-test, we should calculate the t-test statistic.
바이러스를 죽일 수 있는 거예요. 그러니까 이면 우리가 벌써 면역 체계가 생긴 거야, 그게.
So we are doing the t-test. We need to calculate the t-test statistic. Okay, and that t-test statistic can be calculated by the estimation for the parameter. So this is the only information can be used for this parameter, right? And then minus theoretical mean, which is under the null hypothesis. So this theoretical hypothesis is 0, right? And we need to divide this one into standard error. And this is the hardest part when we think about the two independent sample t-test. So this standard error, usually when we have a one sample t-test, we have this one. But now we have two groups, and each group has the sample standard deviation. If we assume that two group has the same sigma, so let me use this one, sigma, then this standard error can be calculated by complicated formula, which is like this. So SP square divided by N1 plus N2 SP square, and then square root of N. Okay, and this SP square can be calculated by this N1 minus multiplied by S1 square plus N2 minus 1 S2 square divided by N1 plus N2 minus 2. So I know this is hard, but we already know what is S1 and then N1 X bar, right? From the data, right? If we have this data, we can calculate the X1 bar, S1, N1, and if we have this data, we can calculate the X2 bar, S2, N2, and then we can use these 6 numbers to calculate this SP square. And once we calculate the SP square, we can just plug that into here, and we can calculate the SE. And after that, we can use this number to calculate the t-test statistic. Okay, so let me just pull up the concrete example, and we're gonna use Sas to calculate each numbers. Okay. So if you go down, I'm gonna use this one and then pull up the Sas screen. Okay, and then I will go to my website to grab the data set. So from here, drag here to the end, and then paste it here. So after submit, so let me just submit this one. And if I see the log, I think, yeah, it just the Sas can load the data without any error. And let me just look at the code that I wrote here. So first, I make a data set name cloud, and then I declare there's a 2 column. One is rainfall, and the other one is seeded. And I using $, I declare that seeded variable is not the numerical, it's a categorical variable, which has the 2 possible options, right? S and U. And log rain can be obtained. I mean, so we're gonna make another 3rd variable whose name is log rain, and this log rain can be made by taking log to the 1st column. Okay, so if since I already submit the code, I can just using proc print data is equal to cloud and run. Then I can see, oh, there are 3 columns, and one is rainfall, second one is seeded, and the 3rd one is log rain. And the reason why we're using the log rain, since we are using the T-Test, which means we are assuming the population distribution follows the normal distribution. I mean, it does not it doesn't need to always follow the normal distribution, but since we are using the center limit theorem, which works really well when we assume that our normal distribution is our population distribution is normal distribution. So if you what is that? Let me see. If you're using, I think that in week 2 we have drawn this G chart. Okay, so using this proc G chart, I can draw the histogram or bar chart for each variable. So if I set the proc G chart data and then V bar for rainfall, and let me just remove the title, and then if I submit this one, I can see the data looks like skewed to the right? But if I take the log to the rainfall, so let me just change this one into log rain, and then if I draw the chart again, I can see this shape, which looks like normal distribution. So assuming our data follows this symmetrical distribution works really well for the test assumption. So we're gonna use this one, right? Okay. And now what I want to do, I want to sort the data. Okay, so I will just go to week 9 again, and then there's a code for the sorting. So if I use the proc sort, and then by seeded means I want this is the reference column for sorting. So let's just submit and then take a look at what has happened. Okay, so if I submit this one and then my result, let me see. Oh, so to check the result of the sorting, we need to use the proc print again. Proc print data is equal to cloud and run. And now we can see from here, from the observation 1 to observation 15, all of them are related to the seeded group. Okay, and from observation 16 to 30, all of them are related to the unseeded group. So we have 15 and 15 data point per each group, right? And then let's see, to do the two-sample t-test, this is we can use the very simple command in Sas, which looks like this, just proc T-test, and then we can declare that our seeded column has information about each group. So class seeded command represent that, and our actual data stored in the log rain, not rainfall. Okay, so if we copy this one and paste into the Sas program, we can see a lot of results, and I want you guys focused on the table. Okay. All right. So this is the two sample t-test table, and our variable is in the log rain, and this means we have 15 for a seeded group, and I mean number of data point. 15 data points are in seeded group, and 15 data points are in the unseeded group, and whose mean and standard deviation also calculated by that command. So we can just use this one, and standard error too. But what I want to do is just write it down, that number, into my note. Okay, so let's just say from the table, what we have is x1, which is x1 bar, which is the sample mean for the seeded group, was 5.0983. Okay, and then x2 is the sample mean for the unseeded group, was 4.0468, and S1 is the sample standard deviation for a seeded group. It was 1.3613, and S2 was the 1.8209, and N1 and N2 was 15. Both of them, we have equal data points for each group. And what I want to do, I want to calculate this SP square. Okay, so SP square is n1 minus 1 multiplied by s1 square plus n2 minus 1 s2 square divided by n1 plus n2 minus 2, right? This one, since we have 15 for each group, data points, number of data points was 15, so these are 14 multiplied by 1.3613 square plus 14 multiplied by 1.928209 divided by 30 minus 2. And if you calculate this one, let me just pause the video and then I'll do the calculation. So if you guys calculate this calculation, the whole thing, you will get this number, okay? And this number is SP squared, okay? And the SE, standard error, is actually that SP squared plus over N1 plus SP squared N2 and take the square root of that, okay? So this is, we have 15 for the number of data, so we have 15 over 2.584407 multiplied by 2, take a square root, okay? And if you calculate this one, you will get 0.5870159, okay? Now what? Now what we have calculated is this one, this SE, okay? So using this SE, we can calculate the T-test statistic, okay? So T-test statistic can be calculated by T is equal to x1 bar minus x2 bar, and this is 0, which is a theoretical mean under the null hypothesis, and then divide by 0. SE, which is 0.5870159, and if you calculate that this x1 and x1 bar minus x2 bar, so I can say this is 5.0983 minus 4.0468, right? And then we have minus 0, so I don't need to write it down, right? So if you calculate this, you will get 1.79. Okay, so this is 1.79 is our T-test statistic. Our degree of freedom is here we have 28, which is n plus 1, n1 plus n2 minus 2. Okay, so degree of freedom is 28, and we can confirm this one in Sas screen. So Sas gave this table, right? We have degree of freedom is 28, and then we have T-test statistic is 1.79, which is the same value we have just calculated, and corresponding p-value is 0.5870159. 0.0841. Okay, so this is the p-value, and let's say our significance level is 0.05. Then can we reject the null hypothesis? Answer is no. Okay, because our p-value is larger than our significance level, which is 0.05, we cannot reject the null hypothesis, which means we cannot say the seeding the chemical into the cloud make a difference when it comes to the amount of the rainfall. Okay. Okay, I think I'm done today. If you have any question about my discussion section, I strongly recommend you give me an email so that we can set up the Zoom meeting for during my office hour. Okay, thank you.